Hello students, today we will talk about one force. The name of the force is something which we often use in some kind of negative connotation many times. Like I had a friction with him, that means I had some kind of argument with him. So we use friction to indicate something has gone wrong. But today we will talk about this force because this is one force that also helps us do several things. Take an example, I will be writing something on board using a pen. That is, I am creating friction between tip of this pen and board. If friction was not there, I would not have been able to write anything, or you also wouldn't have been able to write using your pen or pencil. The tip creates friction. Or when you start pedaling your bicycle, it's because of the friction between tire and ground or road, you can accelerate the vehicle. Same is true even for your car, your motorbikes. So friction also helps. Even when something suddenly comes in the middle and you apply your brakes, what happens? The friction between the rim and pads of the brake, that helps you stop the bicycle. Or same is true for cars and bikes. So friction also helps. Those who have gone to say Jammu and Kashmir or Himachal Pradesh or some place where we have slopy ice, you cannot walk on the ice surface. So you need friction even to walk. You grip your leg or your foot onto the ground and then use that friction to go for next step. So friction helps. But do you know that automobiles, any type of automobile, has to use almost 25% of its energy just countering this friction. So we also have to use more energy to counter the friction. That's the reason perhaps you must have guessed that aeroplanes can fly at a tremendous speed because there is hardly any friction, like with ground what we have. There is friction with air, definitely, but not as much as we have on ground. So once you understand this much, let us know in very brief about this concept of friction. Now when we talk of frictions, normally we talk of friction between two solids. When two solid surfaces interact with each other, there is a force between them which resists movement of one object with respect to other object. For example, if I start pushing this object, the frictional force will resist it. But does that mean there is no friction when I don't push it? There is a friction, but that is equal to the mass multiplied by gravitational acceleration on this object. So that is nothing but mass into g, mg. That is called as normal force. M into g is typically called as normal force. Mass into acceleration due to gravity is equal to frictional force on this object. So, but when, or I can call this as a static frictional force, which is equal to N. But when I start pushing it, it moves after I push it with some force. So how much will be the force to be applied to initiate a motion in this, to counter this friction? What is the frictional force? Is nothing but N into some kind of coefficient of friction between two surfaces, because friction essentially depends on, of course, mass of it, but also type of surfaces and their texture. So if the surfaces are smooth, there will be less frictional force. If they are with a material which is not so smooth, frictional force will be more, and also material with texture of it, that will also decide how much will be the frictional force. So you need to apply some kind of coefficient to understand that frictional force, that is, we'll call as static frictional force. F static is equal to, this is called as mu. It's a Greek alphabet. It is some kind of coefficient of friction, but it is static. So when you are about to move that, look, when it is non-moving and it is causing a friction, you will be talking in terms of static friction and coefficient of static friction. And of course the friction force is also static frictional force. That will be maximum when you apply total force and it starts just about to start its motion, or it is getting into sliding frictional force, then that you will be able to slide it. Always remember, this static frictional force, that is maximum static frictional force, is more than sliding frictional force. Once it starts moving, it is a bit easy to keep it moving. Take an example. If it is a heavy crate, there is a table on which this heavy crate is placed. There is a normal force which is equal to, frictional force. You are trying to pull it this way. So you are applying a force on this, and this frictional force is going in this direction. When this moves, the static force ends. Now it will be frictional force but sliding. Or you could say even kinetic is equal to again mu, but this will be sliding into n. N will remain as it is. See, this frictional force does not depend on surface area which is in contact. You place it this way or this way, frictional force will be same, because the mass decides the frictional force. It is different what we talk in terms of force and pressure. When we talk of frictional force, which is not a real force, which is just a resistance created between two surfaces. Definitely the contact force, because they are in contact with each other. That's the reason frictional force is felt. And how much is this will be decided by the mass. That's the reason I have called it mass into gravity. Gravity is same. So mass times gravity will give you this normal force multiplied by coefficient of either static, or this is static, S stands for static here, or sliding, will decide exact volume of frictional force. I think you are getting the basics of it very clear. So this is higher when you try to push it, and once it starts getting pushed or moving, then it will be far more less than this, because then once this crate starts moving, which is heavy, then you can easily keep pushing it. And what will happen if I add some kind of rollers under this crate? So frictional force of rolling will be sometimes even 100 or 1000 times less than this. So rolling using balls, bearings or cylinders will reduce the frictional force considerably. Maybe as I told you 100 times it will be reduced. So that's the concept of rolling frictional force. So sliding and rolling frictional force. These are two frictional forces when things are in motion. And when it is not in motion, it is static. Now, one more thing can happen, that this is all about frictional force between two solids, also called as a dry frictional force. When it is frictional force in fluids, the considerations are different. And we will try one small activity to understand. See, we know air is also a fluid. So by adding a layer of air in between two surfaces, you can lubricate that surface. That is called as lubricated frictional force. You also do that using oils. You know, on this surface, this stable surface, if I apply oil, sliding of this will become easier. So will happen even with air. So that is lubricated frictional force. So we will not talk about fluid frictional force, just about dry frictional force. If you understand this, I want you to do experiments around this concept like a scientist. Because you know, frictional force can be decided only by experimental method. Because you never know how rough will be this surface. Surface appears or looks to be smooth, but it has microscopic unevenness, and that adds to the coefficient of friction, COF, because that depends on nature and material of two surfaces. For example, if you try to pull one object of same metal from the surface of same metal, like copper on copper, you will apply too much of force, because there is more attraction between these molecules. That means frictional force is basically some kind of adhesion. That is the force, chemical force, that is called as adhesive force between these molecules of any two surfaces. And you have to counter that to pull it. So I think with this much of basic understanding, we'll move on to doing the experiments actually about this friction. We'll be pulling something, taking the readings. We'll try to take the reading just before that object starts moving. That is maximum static friction. And once it starts moving, the reading of spring balance will come down and it will be sliding frictional force. And as I told you that rolling frictional force is too less if compared with sliding, you will get very negligible reading on spring balance. But you must notice all such small things. So these activities, we will also see how air lubricates and air reduces friction. Such concepts we'll see now by experiments. So be a good scientist, observe the things carefully, record them in your notebook. Try to change surfaces. We have given you some couple of options, 2-3 options. But you can use any surface available in your home, like metal surfaces or glass surface or anything else. Try to take more readings and always share such extra readings with us. Try to pull different objects. We have given you one object, but make sure that the object is not heavy. So you should not damage the spring balance. Let us begin with the activities. We will be using spring balance to know the force that we have to apply to pull a specific object. That's how we'll try to know, or we'll know frictional force. So first thing, let's know that this is up to just 100 grams or 1000 newtons. but we need to use it carefully, because if we pull it too much, this will be damaged. Then the first thing, we should adjust this upper zero adjustment strip and bring it exactly to the zero alignment. So this marker is at 0. Now we'll be using this glass piece on top of this surface as a weight. We need to first find out what is the weight of these two things together. What I'll do is, I am using plastic bag of same spring balance, putting a plain sunboard into this, and I am also putting this glass piece into this, and I just hang it to the spring balance and we'll try to get its weight. So never directly do that, always keep it on plain surface and then insert it. Now I'll be holding it up. Yeah, this is showing reading of 80 grams. We'll talk right now in terms of grams because that is easier. So it is 80 grams. Now I'm just taking this out. We will paste this glass piece on sunboard using these adhesive tapes. We have these adhesive tapes. Let us remove the release paper. We need to put a thread to pull it. So I'll start thread right from here itself. The end of thread is put here, and on top of this I am pasting it. Okay, so this joint is done. Let us also remove the release paper from here and paste this thread. Once again I'll put a release paper on top of this. So it will be just sandwiched in middle of it. Won't come out so easily. Now I can pull it. So the pulling is done. So here I'll make a small loop where we can attach spring balance. Okay, so everything is done. In the kit we have given 3 different surfaces. This is a smooth paper, this is a rough board, and this is regular polish paper or sand paper. So as you easily can imagine, this must be really rough. This may be a little bit in between, and this could be smooth. We'll be using 3 surfaces to see how much is the force needed. We know it is 80 gram. So if we really pull it without any additional frictional force, then I should be using 80 grams to pull it. But considering frictional force, there may be some difference. I'll do one thing, I'll begin with wood surface itself. Let us now move the table little bit on this side. And we'll use, this is a spring balance I'm connecting now. We'll use this surface and I'll try to pull it. Take a look. I'm just trying to. So when this is about to move its place, till then static friction is applicable. So it is 25 grams. And when it is being pulled, it will be little less than that. So once again I'll repeat. When it was still to start its motion, you can read it is crossing 20 grams. Almost 25 grams. And when it starts moving, suddenly you will find that pointer moves backward. It comes to 20 grams now. Yeah, it is 20 grams. So static friction showed 25 gram as reading and kinetic or sliding friction showed 20 gram as reading on table surface. Now I will place this on surface of this smooth paper. We'll just hold using one hand like this and will not let our hand touch this sunboard. So let us begin. Look at the static friction first. It starts moving at 20 grams and in motion also it is just 20 grams. Earlier it was 22 grams, now it is 20 grams. We'll have to go once again. No, static friction is more. It is now 35 grams was the static force. Now it is coming to 30. Yeah. So initially when it was yet to move, it went right up to 30. 32, 34, and when it started moving it came back to 30. So difference of 4 grams. But this is not as smooth as the table is. Okay, so this again I'll try on table with when we tilted it this way. Yeah, it is showing similar readings. Little more than before. We'll go for a surface which is rough. This board. Now you observe it minutely. It is crossing 40. Yeah, it went up to 45 and then suddenly the jerky motion started. Take a look. It reached up to 40, 45 and that is the maximum. Static friction is recorded and when it is in motion it is showing 36, 38. So in motion, that is sliding frictional force is lower by 45 is the maximum static frictional force and 38 is the sliding frictional force. And we'll go for the last one, the option of polished paper. I'm placing it again on top of it and we'll try to pull it. Now take a look at the reading of spring, this spring balance. Okay, so it is getting pulled almost 50 is the maximum static frictional force. Yeah, look at it, it has crossed 50 and at 55 it starts moving and comes back to when in motion it comes back to 50 plus and when not in motion it is up to 60 even. So this will of course give you maximum coefficient of friction. So when in motion, now it has gone up to 60 and when motion starts it will come back. You can see it has come back. So what we have understood by doing different activities, normally for wood the coefficient of friction is 0.5. That means if we were applying 80 gram of total force, it is in between 0.25 to 0.5. That is a wood smooth surface of, this is laminate, so it may have a better coefficient as well. So when you pull it, you know that it should have been 80 grams if I straight will lift it against gravity like this. It is 80 grams. But when it is on a surface, you have to multiply this with coefficient of friction. So static friction for wood is normally 0.5 or even less than 0.5. So it will show you figure of 40 grams or maybe 30 grams depending on what is the coefficient of friction of this. You can find it out. Similar way, this also has coefficient of friction about same 40 or so, 0.5 or it is showing 30 grams. So 0.4 would be the coefficient of friction for this. You can calculate this. We have done it on board before. And as the surface changes, the coefficient of friction goes up to 0.6. Normally that is in between, in the range of 0.3 to 0.6 coefficient of friction. But when for certain cases, like when it is a rubber kind of sheet, the coefficient can go even beyond 1 sometimes. This is giving you coefficient of friction about 0.7, 0.8 because it is a very rough surface. This surface is very rough. So giving you higher coefficient of friction. Now one very interesting activity we'll try to do. I'm just taking out some straws from the kit. We make a platform of these straws like this, and we will place this on a platform. Again I am placing spring balance into the hook. Now let us try to move this. Now you will just keep observing the spring balance readings. You will find spring balance may not show any reading. I should use little more number, so in case we have to really move it, but there are few, so I am using it this way. You will find it does not show even any reading. Why? I told you while discussing this topic that rolling frictional force is 100 times less than sliding frictional force. Take a look, it is not showing any reading when it is moving. Because hardly it was 30 grams, when you consider 100 times less, that will be definitely less than 1 gram, and that cannot come on the spring balance. So rolling frictional force is 100 times, even sometimes 1000 times less than sliding frictional force. What we saw so far are the activities around friction between two hard surfaces. Now that is also called as the friction, or that is called as typically dry friction between two surfaces. So they are all about some solids. But when we think of use of a liquid or fluid, then the concepts are altogether different. Fluid can take any shape. So naturally we use fluids in combination with solids as lubricants. You know, grease is used as a lubricant. Even you might have seen even your bicycle. At the chain sprocket joints, oil is put to make it smooth, or at even pedals, that grease or oil is added to make that pedals smooth, or for brakes, and everywhere you may recollect that using some dispenser, that oil is added or grease is added. Now here we will be using in one activity use of air as a fluid. You know, air and water both are fluids, and a film of fluid, if formed between two surfaces, now that implies that two hard surfaces are not interacting directly with each other, but the fluid film is interacting with both the surfaces, and that acts as a lubricant, and that is called as lubricated friction. So one more type of friction is lubricated friction. We will do activity using this hovercraft. Hovercraft is a kind of vehicle which can float, and it has a air between the surface of hovercraft and actual water surface or ground surface. It just rises above and then moves. So it's a cushion of air that gives that reduction of friction, so it can go like aeroplane. Same thing we are doing here. We are creating a film of friction, a film of air to reduce the friction between the surface of this hovercraft and this table surface using these all materials. Let us do this activity, and you can appreciate use of air as a lubricant very much on your own. I don't have to explain anything further. This is a plastic disc with smooth surface on one side and small stem here in the middle. This is a cap which will fit onto this small stem and a balloon. Take a small balloon from the kit. First, put this rim of this cap into mouth of the balloon. Just stretch it mouth little bit so this can easily fit. Stretch this balloon as well, like we often do, and blow it from this through your mouth. Hold using pressure of your thumb like this, so air does not come out. And then press it on top of this center stem. This disc has a hole in the bottom. So pressure from this balloon or air that is compressed in this balloon will come out from here, will spread under this, create some very fine cushion of air between this and table, and being there is a cushion of air, this will become frictionless. There will be no friction between them, or very little friction between them. This air is still pressing. It will start moving. Let us see actual application. We often talk of transport systems. We know we travel by road using cars, buses. We travel using a rail, that is your railway. Sometimes we travel through sea. And that the fourth mode of transport is using aeroplane. So traveling through air. There is one more simple but combination of transport system that is called as hovercrafts. Hovercrafts, that way they look like ships or vessels. But these ships, they do not touch water, they float little above water. Like aeroplane in air, they are ships in air. That is called as hovercraft. What is the science of this hovercraft? Hovercraft has a lot of fans fitted. It takes air from atmosphere, blows it on water surface, and that blow is so hard that entire ship gets lifted, or it hovers over water surface. And then while it is above water level, there is gap between this, or there is a cushion of air between them, two surfaces, and on this cushion of air it moves. So naturally it is without any friction between water and this surface of this ship. There is no friction. That is called as air cushion vehicle, or ACV, air cushion vehicle or hovercraft. We will do a simple model of hovercraft using balloon to press air against some surface.